After sampling, each sample needs to be quantized because each sample could be a real value, a real number. How many bits you need to specify a real number? It's not a finite number of bits. So we need to quantize. In the quantization, you will have some errors, which is quantization error. We will discuss the concept of scalar quantization first, and then we'll move to more complicated quantization methods. So the input signal is first sampled. So a sample which is a real value, x of nts, is a real value. We want to quantize it, but this quantized value, quantized signal also is a real number, but is within a finite set. So XTS is inside a set of values, and these set of values are finite, 5 numbers, 2 numbers, and so on. And once you quantize these sequence of alphabets are encoded into binary stream. So this is called encoder. So now we are only talking about quantization. So this is a block diagram of that. So you do encoding because you want to store it or do other stuff and so on. This is just an example of an 8th-level scalar quantization because we have a scalar input. So let's say this is x of nts, and this is the quantized value x hat of nts. So if your value is between a1 and a2 in this interval, your quantized value, you get this one. If your input value between a2 and a3, you get this value at quantization value. If your input is in this interval, your output is here, and so on. So the output values will become, so these will be in the set of values of the quantized value is either x hat 1 or is x hat 2 or x hat of 8. So the quantized value has only 8 possible values. Scalar quantization is basically the transformation or mapping. Is a nonlinear function. Is a function of the quantized value is a function of the input, but it's just a staircase function. Is the transformation or mapping of one individual sample into discrete value from a finite set, which is a staircase function. So what happens is that you get the set of your values. So your input x of, let's say, nts or x, I don't care about what time is that. Your input value is a real number. So you partition these set, let's say, these numbers up to point A1, I quantize it to one value. From A1 to A2, I quantize it to another value, and then A3 and so on. And then you have A of n minus 1. And then, so here your signal will be quantized to x1 hat, x1. You quantize it to another value, and so you will have in total n interval. So you have to partition the set of real numbers into n disjoint sub-intervals. So you break down your set of values into intervals. So first interval will have one value, second interval the second value, and so on. So the quantization, so for each interval, let's say if you are in the first region, you say that q of x, if x is in the first region, I will have this value. xi is a fixed value. If you are in the second region, you will have the second value, and so on. So it's a staircase function that you could define it easily. If I tell you let's say x1, you know that you are in the first region, but you don't know exactly where in that region you are. So you'll have some errors. Provided that the number of these regions are large enough, your errors is small enough. If this small enough error is acceptable for you and me and everybody else, then we are okay, we can take it. So we need to ensure that the amount of the distortion or error is manageable, is acceptable. So we need to measure it. So one of the popular measures of distortion is the square of the error. So the input value, and this is the quantized value. So the difference sometimes is negative, sometimes is positive. So I cannot just consider the difference. So this is why I put a squared value, so that this distortion becomes always positive. So this is a measure, because the input is random, this is also random, so this is a random. So people, in order to measure it, they calculate the expected value of these. So mean squared error is called distortion. So this is a measure that we measure how much signal is distorted. So we want to make this guy smaller. Obviously, if you have more number of regions, then you could make those regions obviously smaller. Therefore, this mean square error is reduced. However, if you increase the number of regions, then you need more bits. So there is a trade-off. How many bits you are prepared to use and how much distortion you are ready to accept.